Tonight's presentation is about variability, which includes the standard deviation. We've talked about in the past the 5-number summary, which includes the minimum, the maximum, and the 3 quartiles. And that is a popular combination to describe a distribution numerically. But also, an even more popular way to describe a distribution numerically is with the mean and the standard deviation together. Probably the most popular in statistics, and that's what we're going to talk about really tonight, is the standard deviation in association with variability and something called the variance. Measures of variability allow us to distinguish between usual and unusual values. Because sometimes you want more variability and other times you don't. The 2 examples we have here are scores on standardized test or scores on any test. You would not want a large spread. You would want a smaller spread, because that means, people did about the same on the test. Whereas if you have a really low score and a really high score, then that's really not good for that test. Either it means somebody just didn't study, or maybe it was not a very well written test. The same kind of thing with medicine. If 2 people are taking the same kind of medicine, you want it to have around the same variability, because you don't want someone taking medicine and it not doing anything for them, and another person taking the same amount and it messing everything up. Here are some measures of variability. We've mentioned all of them, but we've talked mainly about the range. We've used the interquartile range. We spoke briefly about deviations. Remember, deviation is how far something is from, or how much a measure of data is from the mean. And some new things for us tonight are variance and standard deviation, which we've not talked about. This letter here is called sigma. It is the lowercase form of sigma, because we've already seen the uppercase form, which means sum. There it is that I just drew. This is the lowercase form, which denotes standard deviation, and if it's squared, it denotes variance. These next couple of slides I put in here, these are on the back of the notes that you should have, just to remember and remind you how to enter data into your calculator to get all of these different kinds of things. And so here's the list of instructions, which are on your handout. And the next slide shows a picture of what it would look like if you entered this particular set of data that we have already. So if I enter these numbers, the next slide tells us what each one represents. And so we've used this for the 5-number summary. We've talked that X bar means sample mean. Sigma X, capital Sigma, is just the sum of all the data values. The next one would be the sum of the squared data values. And then we get to this S, which is the standard deviation for a sample. If they use the lowercase sigma, that is the standard deviation for a population. Now, most oftentimes, we will only use the sample standard deviation, because most often we're only dealing with samples. If your data set consists of an entire population, then it would be appropriate to use the population standard deviation. But most of the time, as I've said, the data we're examining comes from a sample, and so in that case we should always use this S sub x. And if you're ever in doubt, it would be a good idea just to use that one. And then this N just represents the number of data values that were in our sample. And then we've talked about the last 5 here. That's our 5-number summary that we have been using with our box plots. This next slide, you may want to kind of jot down this little graphic for your use on your notes. I just wanted to remind everyone of what a deviation is. And so if I have X bar here as my mean, from this data value of 5 to this data value of 7, that is a deviation of 2, because that's the difference between those two. And over here we have a deviation of -4, because from the data value of 1 to the data value of 5 is a difference of -4, so our deviation would be -4. These deviations show how much the data vary about the mean, how far they are apart. And they are the starting point for calculating the variance and the standard deviation. When we first introduced the mean and the median in our notes last week, we talked about how the sum of the deviations is always 0. And that's because the mean is a balancing point for our data. And so because of that, we need another way to calculate the spread about the mean. And so that's where we get into variance and standard deviation. On your note handout, you have a table that you can fill in for the following information. And I did use my calculator to find the mean using one variable statistics in the statistics function of the calculator. And I found x bar to be 28. And I'm reminding you that I'm going to use x bar because this is a sample. Now, to find the deviations, we're going to have to take our data value one at a time and subtract the mean from that data value. So I'll do one for you, and you can do the rest over here to the side. This goes with this. So I take my data value, I subtract off my mean, and this first one gives me -4. Now I do that for each data value in the set. So you can pause the video and do that now for the rest of your table, please. Okay, and once you find all those, you need to take the sum of those deviations, and when you take the sum of those, as we already discussed in this presentation, you should get a sum of 0. If you do not get a sum of 0, you've done something incorrectly. Okay, next I would take each of the deviations, and that's the middle part of the table that you have in your notes when you subtracted, and I square each of those deviations. And what that does is get rid of any negatives that we have, so that when we add them together in a moment, we won't get any more, we won't get a sum of 0. So if I do that and fill in my table, so once you square all the deviations, that will help you fill in the last column of your table. And next, you would take the numbers that you squared, add them up, and divide by how many there are. And that's just finding the average of those numbers that you squared. And when you complete that task, you should get an average of 38.4. So the 384 is just the sum of the squared deviations divided by how many there are. It's just an average. The average of the deviations squared is called the variance. Okay? Now because we squared all the deviations, our units are also squared. So let's say, for instance, our data was like the number of pets somebody owned. 10 people owned this many pets. Well, then our units would be in squared pets if we just use what we found. And that's no good. How can a pet be squared? Okay? So in order to get rid of that, we're going to do something else in a minute. And so the variance is denoted by sigma squared if we're talking about a population, and s squared if we're talking about a sample. Now here's the full formula for the calculation of a variance of a sample, and that's all the steps we just did. We took the deviations, we squared the deviations, we added the deviations, and then we divided by how many there were. Now, notice that this is n minus 1. A moment ago, we only divided by n. Almost always, we will always divide by n minus 1. Now, why do we divide by n minus 1 instead of n when calculating the variance and the standard deviation, as you'll see in a moment? and it's something called degrees of freedom, which we will discuss later on in the year. So you don't really need to know much about degrees of freedom yet. It's coming up later on. Now, variance is very closely related to the standard deviation, and that is the measure of the average deviation from the mean. Okay? Now, as we were speaking of a while ago, we couldn't have a unit that was squared. We wouldn't want pets squared. And so what we do to get rid of that, how do you get rid of a squared? Okay? So for instance, if I had the equation x squared equals 4, what would I do to get rid of that squared on the x? Well, I would take the square root. And so what we're going to do with the variance that we've already calculated is take the square root. So as you see, the formula for finding the standard deviation is exactly like finding the variance, except instead of s squared right here, you have s because we've taken the square root of everything we've done. So we've taken the deviations, we squared the deviations, we added the deviations, we divided by n minus 1, which remember we'll talk about y later, and then we've taken the square root. And dividing by n minus 1 really has to do with what are we doing, a sample or a population. Remember, most of the time we're doing samples. So now we should know how to use this formula, but remember that when you use your one variable statistics in your calculator, when you see S sub x, that's the standard deviation of your data set. So your calculator can help you tremendously avoid having to do a long, drawn-out process of finding the standard deviation, even though it's really not that difficult unless you have a huge data set. Okay, just a few things about the properties of standard deviation, meaning its usefulness. The standard deviation measures spread about the mean and should only be used when the mean is chosen as the measure of center. Standard deviation and mean kind of go hand in hand. If you're talking about the mean, you're probably going to talk about the standard deviation. The second thing is that the standard deviation is always greater than or equal to 0. And if it equals 0, that's only when there is no variability, meaning that this would only happen when all the observations have the same value. The larger standard deviation you have, the larger your variability will be. Which means as the observations become more spread about their mean, the standard deviation is larger. One reason we prefer the standard deviation over just the variance, which we talked about earlier, is because it retains the original units. Just like we were discussing, we don't want to say that our units are pets squared. We'd rather just talk about pets. And one thing to keep in mind is that just like the mean, the standard deviation is not resistant, meaning that a few outliers could make the standard deviation quite large and be deceptive. In fact, the only measure of variability that is resistant is the IQR. All the rest of them are not resistant statistics. And the rest of your notes that you have will be covered either in class tomorrow or on a video tomorrow night.